let's consider an example where we try to find the coefficient relationships and the Maxwell relationships for an actual thermodynamic function. And let's use the combined first and second laws, which is du is TdS minus PdV plus mu dN. So the first thing that we want to do, step one really, is to figure out what u is a function of. Right, so we can see that u is a function of s and v and n. And then the second step will be to write the total differential. So du u equals, so this is the partial of u with respect to s at constant v and n times ds plus du dv at constant s and n dv plus du dn at constant s and v dn. So the third step, and it's sort of useful to be able to see this, which is why I'm going to try to keep it here. So the third step is to do the coefficient relationships. So we are going to compare this expression with this expression to get the coefficient relationships. So if we compare them, we see that this stuff right here is equal to t. So t is du ds at constant v and n. Now, you might not feel like you need another way to define what temperature is, but this is another way that we could describe temperature, right? So it's how the internal energy of a system changes as its entropy changes. That's another way that we could describe what temperature is. We can compare the two starred equations again to see that this stuff here is equal to negative p. So negative p is du dv at constant s and n. And finally that mu is equal to du dn at constant s and v. So if we're looking to understand what is chemical potential, this is one of the definitions. It's how the internal energy of the system changes as we add more stuff. To look at the coefficient, or rather the second derivatives. And for this, we are going to need those coefficient relationships. So I'm just going to write them down again so that we have them here. So we had that for T, we have this for P, and we had this for chemical potential, which was du dn at constant S and V. So U, remember, was a function of S and V and N. So when we're taking the second derivatives, we can take it with respect to any two of these. So we could do S and V, or V and N, or S and N. For this example that I'm going to do here, I'll focus on just S and V, but you could do it for any of them. So let's start and let's do the derivative with respect to V of du ds. And this is at constant N and V. This is at constant N and S. And then we're going to switch the order over here so that we do the derivative with respect to S. of du dv. This is at constant n and s, and this is at constant n and v. So the coefficient relationships come in here because I can replace this stuff with, if we look up here, t, and I can replace this stuff up here with negative p, which then allows me to write that dt dv at constant n and s is equal to negative dp ds at constant n and v. Okay, so right now this just looks like a bunch of math and might not have very much meaning to you, and we will work on that in time, but what this allows us to see is that the way that the temperature varies as the volume changes. So if I squeeze on this thing, does its temperature go up or down, is mathematically equal to negative how the pressure changes as entropy changes. So again, this one is not particularly intuitive, but we will work through some other examples in class where we come to more useful relationships from the Maxwell relationship. But this is an example of how it works, and sort of this expression right here, this is one of the Maxwell relationships for you. If we do the second derivatives of v and n or s and n, we would end up with the other two.